Electricity cannot be stored. Production must correspond to consumption, placing demands on the transmission grid. Denmark's geographical location between the European continent and the rest of Scandinavia is of considerable strategic importance as far as electricity transmission is concerned. Denmark is situated between two large electricity transmission grids. Zealand and the other islands in eastern Denmark are, together with Norway, Sweden and Finland, connected in one synchronous grid, while Jutland and Funen are connected to the Central European grid. Eltra is responsible for the overall security of supply and plans, builds, operates and owns the transmission grid. This film focuses on the western part of Denmark, for which Eltra is responsible. The transmission grid is a 400 kilovolt, that's 400 kV grid of ring connections which are connected to the primary power stations in Åbenrå, Fredericia, Esbjerg, Odense, Aarhus and Aalborg, as well as to Germany. The connections to Norway and Sweden are DC connections. There are two important nodes in the 400 kV grid where the connections to Norway and Sweden start from: Kjell near Viborg and Vesterhassing near Aalborg. The 400 kV transmission grid in Jutland and on Funen has been built up from the mid-1960s to the 1980s. Already at the end of the 80s, Eltra was seeking permission to build the line from Aarhus to Aalborg in order to complete the 400 kV ring. This would significantly reduce the vulnerability of the grid to major faults. Moreover, it would increase the possibility of transmitting large volumes of power through Jutland. In the 1990s, an agreement was signed with the Danish authorities on principles for the establishment and restructuring of high-voltage circuits. It meant that 400 kV transmission lines could still be constructed as overhead lines. However, sometimes shorter cable sections could be laid in urban areas as well as in areas of special natural beauty. It was also agreed that in connection with the expansion of the 400 kV grid, an attempt should be made to reorganize the 60 kV and 150 kV grids. This could happen partly by decommissioning lines and partly by bringing together the circuits and suspending them on fewer towers. This approach has been followed with the establishment of the 400 kV connection between Aarhus and Aalborg, which was commissioned in 2004. In order to be able to construct the 400 kV connection between Aarhus and Aalborg, the following conditions had to be met. The line had to be routed west of the woodlands of Roldskov along the motorway. An existing 150 kV overhead line between Aarhus and Aalborg had to be removed. The overhead lines around Aalborg had to be reorganized. No new overhead lines would be established across Mariager Fjord, in Gudnådalen at Randers, or through Inkildedalen south of Aalborg. The existing overhead lines across Mariager Fjord, Gudnådalen and through Inkildedalen had to be removed. These conditions meant that the three sections of the 400 kV line had to be established as cable connections, 14.5 kilometers in all. At the same time, the parallel 60 kV and 150 kV lines also needed to be run underground. The three cable sections were Gudnådalen, Mariager Fjord and Inkildedalen. The Gudnådalen Valley is approximately 3 kilometers wide at Randers. The river itself is 100 meters wide, and the valley floor is very flat and wet. Mariager Fjord is approximately 700 meters wide, with a maximum water depth of 12 meters. It has a soft floor, the upper layer of which consists of organic material. The inlet suffers from oxygen depletion, and particularly stringent environmental requirements were set on the part of the authorities. Several thousand years ago, Inkildedalen was also an inlet. It is now agricultural land, but there is an idea it might be used as a green recreational area in the future. The soil is very wet. The three cable sections are part of an overhead line with considerable transmission capacity. Each 400 kV overhead circuit consists of duplex steel reinforced aluminium conductors with a cross-sectional area of 772 square millimeters. The standard transmission capacity of such a circuit is 2,760 amperes. The standard conditions are air temperature of 20 degrees C, wind speed of 0.6 meters per second, irradiation of 900 watts per square meter. The cable sections are dimensioned on the basis of current requirements, not on the basis of the possibilities offered by the overhead lines. This means that the cables in the 400 kV connection restrict transmission capacity. However, the cables have been dimensioned so that in practice they do not cause congestion. In the tender documents for supplying cables, the requirement was for a transmission capacity of a minimum of 2 × 700 amperes under standard conditions, which are: the cables are buried in the ground, the cables are laid at a depth of a minimum of 1.2 meters, thermal resistivity of the surrounding soil is 1 Kelvin meter per watt, the soil temperature is 15 degrees C. The cable connections should be installed as double cable circuits. In other words, 2 cable circuits are laid in parallel with a spacing of 6 meters. This achieves the following: the potential for large transmission capacity for the completed circuit without having to purchase expensive cables with a large cross-section. Considerably improved security of operations. Should a fault occur on one of the circuits, in the space of just a few hours, it can be disconnected from the grid and the line can continue to operate at half transmission capacity until the cable has been repaired. The requirement for a continuous transmission capacity of only 700 ampere for each circuit assumes that the cable can be subjected to a significantly higher load for several hours if the previous load has been lower than what the cable is actually designed to carry. And this is nearly always the case in practice.